Hey, this is Chris Kopik for Intagma. The idea for this setup came from a question on our Patreon community hub, where I've been mainly publishing the course on kin effects over the last year. But since this effect can be quite easily achieved just using Vellum, we're publishing it here on YouTube. So the question was how we'd go about recreating an effect like in this beautifully executed project by Playback Design. And again, this is quite easily done using Vellum and blending some rest length. So let's jump into Houdini and get going. With these sorts of setups, it's usually a good idea to work on a single ribbon first and then apply this to lots and lots of copies. So let's just do that. First of all, let's of course drop down a geonode, dive inside, and first of all, I want to drop down a grid. This will be my ribbon. On my grid, I want to set the size to a value of 0.2 by 1. I want to move it over a bit in the Z direction by a value of 0.5, so that one end is right here at world origin. And I want to change up the rows and columns, or the rows to a value of 47, so I get roughly square divisions on my ribbon here. Also later for rendering, let's just drop down some UVs by using a UV texture node, wire this in, and to get the proper orientation, let's set the Y scale to a value of -1. Now from this simple geostream here, I want to branch out and I want to create two versions of my ribbon. One that is bent just slightly and one that is curled into the curls that we're looking for. So let's do just that. Let's drop down a bend sub. Let's switch to a handles tool so that we can see what we're doing. And let's first of all tweak the capture parameters a bit. So the capture origin, I want to move forward a tiny bit. So let's add in a value of 0.1 so that this part right here at the end remains stationary. And then I want to add a tiny bit of offset to the capture direction, a value of -0.02. So that if I increase the bend angle and I increase it a whole lot, I get this curl right here. But this is the version of a ribbon that is curled just a tiny bit. So let's set the value, let's say, to a value of 13.7. That worked nice for me. Something like this. Let's create a second version. Let's just duplicate our bend node right here. Let's set the bend in this case to a value of 1080 degrees, something like this. And I think this is curled a bit too much, so let's reduce it a bit by increasing the capture length to a value of maybe 1.91. Something like this looked fine for me. Now let's turn both of these streams into Vellum objects. So let's drop down a Vellum cloth. And on my Vellum cloth, let's adjust the parameters. First of all, I want to set up some pinpoints. And in this case, I think I just want to grab the first two rows. Something like this. And scrolling down to the band, I want to increase the band stiffness or the multiplier for the band stiffness a whole lot to a value of 0.1. And this will give our band constraints enough strength to curl into this spiral. I want the exact same Vellum settings for my other geostream right here. So let's create a reference copy, and I can create a reference copy by holding Ctrl Shift at Alt and then just dragging my Vellum cloth node. And now I get a copy of my node where every parameter is a relative reference to this node right here. So they both linked. And now we have two Vellum objects. And the main difference between those two Vellum objects, and let's maybe switch back to a camera view, is of course the shape, but also the rest lengths on those two objects. And if you know Vellum, you know that those rest lengths on those constraints are the main driving factor behind the shape of a Vellum object or of a Vellum simulation in the end. So my idea here is, since these two objects have the exact same topology, the exact same number of constraints and points and so on, I can just take the rest lengths of this curl state right here and copy them onto my main ribbon right here. And then later in the Vellum solver, just blend between the original rest lengths and the curled rest lengths right here, and therefore make my ribbon curl into a spiral. So let's do this. Let's first of all copy over the rest length of this geostream right here to this one right here. So for this, let's just use an attrib copy. Drop this down. Let's wire in the constraint geometry of our main Vellum object right here and the constraint geometry of a goal Vellum object right here. And let's first of all set both groups to primitives since we're working on primitives. And we want to copy over not our CD attribute, but our rest length. And we want to rename it, and let's call it rest length underscore goal. So let's take a quick look at the geo spreadsheet and let's see what happened here. So on this geostream, on our constraint geometry, we now have 3 rest lengths. We have the main rest length, which is fed to a Vellum simulation. Then we have the rest length goal that we brought over. So this is our curl state. And then we have the rest length original, which is right now the same as our main rest length right here, and is the rest length that we're starting out. So our straight or uncurled state of our Vellum ribbon. So my main idea here is inside a Vellum solver, set up a little wrangle and then just set the rest length to a blend between a rest length original and a rest length goal. And if our blend is closer to a rest length goal, it will be curled, and if it's closer to a rest length original, it will be straight. So let's try this. Let's maybe make some room here. Let's wire this into a Vellum solver. Our main geo goes in here and our constraint geo goes in here. For a solver, let's set up a ground position and let's move it a tiny bit down, a value of minus 0.01. And then let's jump inside and let's drop down a geometry wrangle. Let's first of all set this up. We want to run over primitives because all our constraints are primitives. In the data bindings, we want to run over not our main geometry, but our constraint geometry. And now, inside our code field, let's write our code. And for now, just for testing, this will be a simple one-liner. So in the end, we want to modify our rest length. So let's grab f at rest length. And this should be equal to a blend, or in Vex terms, a linear interpolation, or lerp for short. So lerp between our rest length our original rest length, and our rest length underscore goal, or curled rest length. And as a blending factor, and let's make some room in here, I want for now a simple slider. Let's create a float slider and let's call it blend. Let's close all our parentheses, let's add a semicolon, and let's hit this button right here to create our blend slider. So now with this setup done here, let's add a simple animation. Let's maybe wait until frame 10, until we start animating. Then let's add a keyframe to a blend slider, and then let's maybe move to frame 50 and set the slider to 1 and add another keyframe. Let's test this, let's jump back out and let's sim this. And we see a ribbon sort of deforming and sort of struggling to curl into a spiral, but it's not happening right now. And the reason it's not happening is for these very strong band constraints, we also have to increase our constraint iterations a whole lot to make them strong enough. So in this case, let's just increase them tenfold. And also to give our ribbon a bit more help, I also decreased the gravity, in this case to a value of -4. Let's try that again. And now our ribbon is curling up nicely. So this is the main part of our setup done. Let's just now work on creating multiple copies of a ribbon and controlling them not with a simple slider, but with an attribute so we can get more variation. Let's disconnect our Vellum solver for now and let's work on creating copies of our main Vellum object. And for this, first of all, I want to pack it. Let's create a Vellum pack, where in both our main geometry and our constraints, and now we have them just in a single geostream. And I can wire this, for example, in a copy to points, which I'm going to copy a little later. And then I can use a Vellum unpack to get my streams back and wire those into my Vellum solver. But let's for now work on our copies. For my copy object, I want to be a bit lazy, and I just want to use a spiral to get something that sort of looks like phyllotaxis. And on my spiral, I want to set up 6 turns. I want to have an increase by turn by just a value of 0.1. And I want to have a fairly high number of divisions per turn. Let's set it to 250. And we get this spiral right here. Right now we have the problem that our points in here are very tightly packed, and up here, right at the end, they are a lot looser. So let's just make them even with a resample node. And for the size of our ribbons, a value of 0.1168 worked nicely. And also while we're at it, I want to create a curve view attribute that I'm going to use later to drive the curling and uncurling animation. Next, for our copy to points to work, let's also create some normals on these points. And this will be a very simple wrangle again. And I just want to have the normals point outward from the center of a spiral. And this is quite easily done by, first of all, modifying our normals. And our normals should just be unnormalized v at p vector, the position in space. And if I turn on normal display, now they're just pointing out. Let's wire this into our copy to points. Let's see how this looks. And maybe just take a look at the Vellum unpack and maybe turn off point and normal display. And yes, this is looking fine. So now on this GeoStream right here, I want to create a point attribute that will later drive our animation, essentially turn our slider from the first example that we built up here. And I basically want to start inwards from a spiral, curling all those ribbons in, and then later, starting from the end of our spiral, flattening all our ribbons out again. And I want to do this in a simple point warp. Let's jump inside, and what I mainly want to do here is to drive a gradient from the inside of our spiral outside and then from the outside back in again. And for this, first of all, I want to use my curve view attribute that I created earlier. So let's bind it in, import our curve view. And I also want two parameters. So let's drop down two parm nodes. And the first one should be the position of my gradient on this curve. Let's call it pause. And the second one should be the width of the gradient. And let's call it width. And for the width, I want a default value of 0.1. And if we jump back out, now we should see these parameters also here on our warp. And the sort of classic way to do this is to just drop down a fit range and wire in our curve view. And then in the min position, let's wire in our pause. And for the max position, let's wire in our position and our width added together like this. And just to view this, let's just wire this into the color output. And now if I jump back out and I move the pause slider, I can drive the color and also therefore later our animation on our curve. Let's change a few things up. First of all, I want to invert my color because black should mean the straight state of our animation and white should mean the curl state. So on my fit range, let's just invert the min and max like this. And let's also write that not just a color, but also an attribute that I later want to use. Let's use a bind export and call our attrib anim like this. And let's wire in our output here as well. There's one thing that's annoying me a bit, and that is even though out here my position value is at 0, some points are already white, so already in their curl state, and that just increases. But if this value is at 0, I want every point in here to be black and not those first few points to be white. So let's quickly fix this as well. And this is quite easily done by making a bit more room here before first fit and by dropping down another fit range. And in here, let's wire in as an input, first of all, our position. Then this goes into our second fit into the minimum position like this. And also in the add node, so we're basically replacing all connections from a pause node with this fit node. And then let's also drop down a multiply constant and let's take the width in there. Let's multiply it by -1 and then wire this in the destination min of this fit node. Let's reorder our stuff a bit here to make this a bit clearer. This is our warp in the end. And if I jump back out, if I start at 0, every point is black. And if I move to 1, every point is white. So this is exactly what I want. Let's wire this into a copy to points. And on our Vellum unpack, I want to also transfer this anim attribute to my geometry like this. So now this slider is essentially my control for my animation right here. And let's set up a simple animation. For this final setup, I want to set my frame rate to a value of 25 because this is what I used. And let's start out at a first frame of 25. Let's add a keyframe at 0 right here. Then let's move to frame 150. Let's set a value here to 1. Let's make a timeline a lot longer. Let's say 350 frames. Let's move to frame 175. Add another keyframe right here, again at 1. And then move to frame 250 right here. And again, set a value to 0, like this. So we got our Vellum geo set up. We got our animation attribute set up. Let's finally work on bringing this attribute into our Vellum solver and driving the animation with this. So first of all, let's wire in our Vellum solver. In this case, on my Vellum solver, I also want to increase the collision passes since we have a lot of collisions in here. And let's say we want a value of 40. And also for my PC, since I got 64 gigabytes of RAM, I increased the cache memory to a value of 50 gigs. But this is of course dependent on your PC specs. Now let's make sure we can grab the anim attribute inside the solver, because this solver will just grab the first frame and stick with this. So let's create another branch here. Let's create a null, call this anim, and wire in our constraint geometry in here. And if we take a look at the geo spreadsheet, we should see that our anim attribute is on point level and we want it on primitive level, of course. So let's promote it from point to primitive like this. Now let's jump into our solver. Let's take a look at our wrangle again. And in this case, first of all, we need to set up another input. And in this case, on input 2, I want to grab a SOP. And this SOP will be our reference that we called anim. And inside our code, we want to replace this value right here with our animation value. So anim. And we have to grab this value. And in this case, our float anim will be a primitive attribute on GeoStream1 called anim. And we're looking at our current primnum that we're processing here, like this. So let's jump out and test this. And of course, our simulation now runs a good bit slower, but let's just wait for it and see if something happens. And at this point right here, right around frame 52, we should expect to see some curling starting, but we don't. And this is for a reason that's somewhat hard to find, which is the reason that our Vellum simulation, and I think in moving our simulation geo to our GPU and back, Vellum is changing the primitive order on our primitives. So the references that were set up here don't work in here, or they're landing in the wrong places. There is a simple fix for this. In our wrangle right here, we don't just want to rely on a simple primitive number right here. We want to rely on an ID attribute, and let's create this. Let's drop down an enumerate sub to create our ID attribute, and let's wire this in on both our constraint geostreams. And the type should be primitive again, and the attribute should be called ID like this, and it should be an integer. And now in our geometry wrangle inside our solver, we want to grab the prim that we're looking for, and we want to grab it by the ID to prim function. And this should look on GeoStream1. And our ID attribute is I at ID like this. And then in here, let's not use a primnum. Let's just use the prim variable that we created up here like this. And now this should work. Let's jump back out. Let's play animation and let's see if something happens. And yes, indeed, now our ribbons start curling in. And since this is a fairly slow Vellum simulation right here, I can just drop down a file cache, wire this into my Vellum solver. Let's set the file path to explicit. We can leave the file name right here as is, and then just hit save to disk and maybe drink a coffee or something. So this is it for today. This is how to build this Vellum curling ribbon setup. One thing that you might want to explore in this setup is changing out this anim attribute right here. And this could, for example, be just as well a mobs offset if you're a fan of the mobs toolset. This is just the simple example that I used for this setup right here. But of course, you can use whatever you want in here. So this is it for today. I hope you liked this, I hope you have fun experimenting with this, and until next time, it's cheers and goodbye.